Have you ever marveled at digital humans in a blockbuster movie? Maybe a cutting-edge video game, or even a detailed medical simulation. They often look incredibly real, don't they?
Oh, absolutely. Your brain just accepted them. Almost real people.
But here's the surprising twist. Even the most advanced computer vision models, the ones behind these seemingly perfect digital bodies, they frequently create figures that move in ways no real human ever could. Imagine a knee bending sideways, maybe, or an elbow twisting at some impossible angle. It's subtle, maybe, but a really profound imperfection.
It is. It's a critical limitation, actually, that has quietly plagued many of the most sophisticated computer vision models. Visually, yeah, they might pass muster.
Right.
But when you look closer, their movements often defy the fundamental rules of human biomechanics. They're basically breaking the laws of anatomy.
And today we're embarking on a deep dive into a groundbreaking innovation that is finally bridging that very gap. We're talking about reconstructing digital humans with not just visual accuracy, but biomechanical accuracy.
That's the key.
Our mission today is to pull back the curtain on HSMR. That's human skeleton and mesh recovery. It's a powerful new method that reconstructs complete 3D human models from just a single image.
From one picture, yeah.
We'll explore how it leverages a unique, really revolutionary model called Skell, and what makes this whole approach such a game changer for understanding human movement with, unprecedented precision.
And this isn't just about crafting prettier digital avatars for, say, entertainment, though that's definitely a fantastic side effect.
Sure.
It's really about building digital humans that move authentically, respecting the very limits and, frankly, the extraordinary capabilities of our own bodies. Think about the implications beyond just movies and games.
Absolutely. So whether you're fascinated by the future of animation, maybe curious about how AI can revolutionize physical therapy, or you simply love a good aha moment when tech tackles a seemingly impossible problem, well, understanding this work opens up a captivating world. It's where cutting-edge tech truly meets anatomical exactitude.
A really neat intersection.
So let's start with the why. What's the underlying problem here that HSMR is setting out to solve? For years now, we've seen truly incredible progress in 3D human pose estimation.
A remarkable progress.
We have widely used models like SMPL, that's skin multi-person linear, and its extensions, like SMPLX and GHUM. These models are like staples in fields like graphics, animation, AR, VR.
Standard tools, really.
They're good, really good at making digital bodies look human. So if they're so capable, what's been the big holdup? Why haven't they been fully embraced in areas that demand, ultimate precision?
That's the crucial question. Despite all those advancements, there's been this significant persistent gap. Limited adoption within fields that demand real scientific precision, like biomechanics.
Why is that?
Well, the requirements in biomechanics are just far more stringent. They need digital human models that can estimate parameters fully compatible with real biomechanical skeletons. Models that respect the natural limits of human joints, guarantee physically plausible motion, and provide highly accurate estimates every single time. And most existing computer vision methods, including that whole SMPL family, they just don't satisfy these needs, not without extensive, often manual post-processing.
So extra work, extra time.
Exactly, which adds immense time and complexity, making it impractical for many applications.
And here's where it gets really fascinating, I think. The core issue isn't just some minor oversight. While these SMPR family models offer plausible surface representations, meaning the skin and overall shape look pretty good,
Visually convincing, yes.
their underlying skeleton design is fundamentally not anatomically accurate. It's kind of like creating a perfect visual replica of a car, but when you try to drive it, the wheels can turn backward or fold in on themselves.
Right, it just doesn't follow the laws of physics or mechanics.
Exactly.
The kinematic tree, which is basically the hierarchical map of how body segments and joints connect and move it, doesn't accurately reflect a real human skeleton. Not properly.
How so?
Instead of mirroring the true mechanics of our joints, these models often use simplified ball joints pretty much everywhere. Think of a ball joint like allowing full rotation in any direction.
Okay, like a shoulder.
Exactly. That's true for a shoulder or a hip, sure. But using them everywhere introduces additional degrees of freedom where they simply don't exist in the human body, like the knee or the elbow.
And the consequence of that is profound for anyone needing scientific accuracy, right? It leads to the prediction of unnatural, impossible joint angles.
Totally impossible sometimes.
The outputs are fundamentally incompatible with serious biomechanical analysis, with simulations. Let's take the human knee, for instance. A real knee, it primarily allows for flexion and extension, just bending and straightening. That's basically 1 degree of freedom, right?
One main degree of freedom, yes,
Yeah.
with very defined limits.
Yeah, like 0 degrees for full extension and maybe about 135 degrees for full flexion, something like that. But in the SMPL model, it's often treated as a bowl joint with 3 degrees of freedom.
Which means it can generate rotations that a real knee absolutely couldn't perform. Bending sideways, twisting unnaturally, things that would cause serious injury in a real person.
Wow.
So while the 3D joint positions might appear close to reality on screen, the way the body parts are oriented or rotated around those joints can be completely wrong from a biomechanical viewpoint.
And for a medical simulation, or training a robot, or analyzing an athlete's gait, that's a critical flaw.
It's a showstopper. You
Yeah.
simply can't trust the data if the underlying mechanics are wrong.
Which brings us perfectly to the what? This is where HSMR, human skeleton and mesh recovery, steps into the picture. It's presented as the first fully automated end-to-end approach that can reconstruct humans in 3D from just a single image
Right.
by estimating the precise parameters of a specific groundbreaking biomechanical skeleton model.
Right.
And that model is called SKEL.
Okay, let's pull apart this crucial innovation. The SKEL model itself. SKEL, the name comes from the paper From Skin to Skeleton, towards biomechanically accurate 3D digital humans. It's a really pivotal academic development.
So it's built on solid research.
Absolutely. It takes the familiar SMPL surface mesh, which, as we said, is great for the skin's shape, and fundamentally integrates it with a true biomechanical skeleton model, or BSM.
And the key distinction here, this is the real breakthrough, isn't it? SKEL meticulously designs its kinematic parameters, how each part moves relative to another according to the real human biomechanical structure.
Exactly. It only models the realistic degrees of freedom for each joint.
So where SMPL might see a knee with like 3 potential ways to rotate.
SKEL correctly limits it to just the one, that main flexion-extension axis, and crucially, with those predefined biologically accurate ranges built right in.
That thoughtful design has a profound impact then. It results in what the researchers call lower dimensional pose parameters.
Right. SKEL uses 40 size parameters to define a pose compared to SMPL's 72. But here's the real genius, the academic leap. Each of SKEL's pose parameters corresponds to a single realistic degree of freedom.
1 movement, 1 parameter.
Precisely. And it comes with explicit, built-in joint rotation limits. This isn't just about reducing numbers. It's about mirroring exactly how a real body works. It puts an end to those bizarre, impossible twists we saw in the older models.
That's a fundamental shift. A significant academic contribution for sure, especially for real-world applications needing precision.
Absolutely. It's designed for biomechanical accuracy from the ground up.
Okay, so SKEL provides the anatomically correct blueprint. Fantastic. But that raises a massive question, doesn't it? How do you even begin to train a deep learning model like HSMR to work with it? Especially when, as you implied, data for such a specialized biomechanically accurate model just doesn't exist.
It doesn't. Or rather, it didn't. And that sounds like an enormous challenge.
It sounds like a showstopper itself.
It absolutely was. And what's academically fascinating here, really core to the innovation, is that this complete lack of any existing dataset images paired with their corresponding SKEL parameters was the major hurdle.
A common problem for new models, I guess.
Very common when you introduce novel, highly specialized model. You have this revolutionary concept, the SKEL model, but no ground truth data to teach your AI system how to use it effectively. The researchers, Xia, Xiaowei, Etienne, Vouga, Qixing, Huang, and Georgios, Pavlakos, they had to get incredibly resourceful.
So how did they tackle it? What was the innovation?
They developed this really clever multi-stage pipeline. Their first major innovation was generating something they called pseudo ground truth.
Pseudo ground truth, so like fake but useful data.
Kind of, yeah. Imagine you need perfect, true data, the ground truth, to teach an AI. But that didn't exist for SKEL. So they created imperfect but incredibly useful estimates. That's the pseudo part.
Oh.
They cleverly leveraged existing data sets that already had estimated SMPL parameters. Lots of data exists with SMPL estimates, and they developed a process to convert those SMPL estimates into initial SKEL pseudo ground truth.
Ah, because they share the same surface mesh.
Exactly. That shared surface topology allows for an optimization process. They basically try to find the scale parameters that best match the shape produced by the known SMPL parameter.
Clever. But you said initial and pseudo. Sounds like there's a catch.
There is, and this is where the next innovation becomes critical. This initial conversion from SMPL to scale is, well, by its very nature, an imperfect procedure.
Right, because the underlying skeletons are different.
Precisely. It can have frequent failure cases. It's like trying to perfectly force a slightly differently shaped peg into a hole, even if they seem similar overall. The initial precision just isn't guaranteed.
Okay, so how did they fix the imperfect pseudo data?
To elegantly address this inherent imperfection, HSMR introduces its second major innovation, an iterative refinement routine during training. They brilliantly dubbed this process Scalify.
Scalify, like S-amplify, but for scale.
Exactly. It's an iterative process, kind of like a sculptor refining their work over time. This process progressively improves the scale pseudo-ground truth throughout the network's learning phase. It gets better as the main model gets better.
How does that work, refining the estimates?
The mechanism behind Scalify is quite elegant, actually, and really significant from a research standpoint. It periodically takes the network's own current scale estimates as a starting point,
Okay.
and then it iteratively optimizes those parameters by trying to make them better align with the 2D key points like joints detected in the original input image.
Ah, so it uses the 2D image evidence to fix the 3D estimate.
Right. It's this continuous feedback loop. It helps the main model learn to produce more accurate and, crucially, more biomechanically sound outputs with each training cycle.
And vital for guaranteeing that biomechanical accuracy, that physical realism, is a key component built into Scalify, something called a pose prior.
Yes, the pose prior. Think of it as an invisible biomechanical guardian, or maybe a strict rule enforcer.
How does it enforce the rules?
Well, if the model, during this refinement, tries to bend a knee beyond its natural anatomical range, or twist an elbow impossibly.
Like the old models did.
Exactly. This prior immediately intervenes. Mathematically, it penalizes those impossible rotations. It gently pushes the joint back into a movement a real human body could actually perform.
So it bakes the anatomic limits right into the learning process.
Precisely. It's absolutely vital for ensuring the realism and physical plausibility of the final output, preventing those impossible contortions we talked about.
Okay, that's the data side. What about the AI model itself, the architecture?
Right. From an architectural standpoint, HSMR employs a modern, sophisticated type of AI network. It uses what's known as a transformer-based network.
Ah, transformers are everywhere now.
They really are. They've transformed various fields of AI. In HSMR, they use a specific kind, a visual transformer or VIT backbone with a transformer head. This system takes the single RGB image as input and directly estimates the parameters of the scale model, the camera view, the person's body shape, and their precise pose, all encoded in those 46 scale parameters.
So it maps image to biomechanical pose directly.
Yeah, it's a highly efficient and effective approach for this kind of task. Learned end to end.
Okay, there's one more technical detail mentioned, something about rotation representation. It sounds a bit complex.
Ah, yes. That really underscores the academic rigor here. Even though Scale's pose parameters are ultimately represented in a common format called Euler angles.
Which can sometimes be tricky for networks to learn directly, right?
Exactly. The researchers found that directly predicting Euler angles with a neural network led to a clear drop in performance. It's a known issue called gimbal lock, among other things.
So what do they do?
They implemented a clever workaround. They have the network initially estimate rotations using a different format, a continuous rotation representation, which is mathematically more stable for neural networks to handle.
Oh, okay.
This stable representation is then converted internally into a rotation matrix format, which is good for applying the learning rules, the losses, and only then, finally, is it converted back to the Euler angles needed for the scale model itself.
Wow, that's quite a juggling act.
It is, but it's an ingenious method that ensures better accuracy by using the mathematically nicest representation at each stage of the process.
Okay, so all these innovations, the pseudo-ground truth, the Scalify refinement, the pose prior, the transformer architecture, the rotation trick, they all lead us to the impact. How does HSMR actually perform? Does it deliver on this promise of biomechanically sound reconstruction?
Well, the results are quite striking. Despite using Scale, which is technically a less flexible model, remember, fewer, more constrained degrees of freedom compared to SMPL.
Right, it can't cheat by bending impossibly.
Exactly. And despite starting without any direct, perfectly labeled ground truth data for training, HSMR achieves incredibly competitive performance on standard benchmarks.
So it keeps up with the less constrained models.
It largely matches the performance of state-of-the-art methods like HMR 2.0 on most standard datasets, like 3D PW and human 3.6M. We're talking only up to maybe half a millimeter difference in accuracy on average.
That's amazing considering the added constraints.
It really is a truly remarkable achievement. It shows the power of the approach.
But you mentioned challenging poses earlier. Does it do better there?
Yes. And here's where it really sets itself apart and shows its, well, academic strength, you could say. HSMR truly shines in challenging settings. Extreme 3D poses, difficult viewpoints.
Like yoga poses.
Exactly. On the MAOAO dataset, which specifically includes complex contorted poses like those found in yoga, HSMR shows a massive improvement, more than 10 millimeters better accuracy compared to other leading methods.
10 millimeters. That's a huge leap in 3D pose estimation.
It's a very significant leap, yes, especially for movements that are historically difficult for traditional models to capture correctly.
And the why behind that big improvement? Is it the Xiaol model?
It's directly attributed to the stronger pose regularization that the biomechanical skeleton imposes. Because Xiaol inherently only allows realistic degrees of freedom, it simply prevents the model from predicting those unnatural but numerically close poses.
The ones that might fool a simple error metric but look wrong to a human or a biomechanist.
Precisely. Xiaol has that anatomical knowledge built in, acting as a constant guide towards realism. It's built-in wisdom, you could say.
And the empirical evidence. Do they show proof that it avoids those unnatural angles?
Oh, absolutely. The paper provides profoundly compelling data. Clear, quantitative results showing how previous SMPL-based methods frequently violate joint angle limits, leading to truly unnatural rotations.
Got an example.
Yeah, get this. HMR 2.0, a leading method, when tested on that challenging MOYO dataset, showed that 47.6%, almost half, of its left elbow rotations exceed 10 degrees of unnatural bending.
Almost half the time the elbow bends the wrong way. That's unusable for biomechanics.
Pretty much. Imagine trying to analyze an athlete's throwing motion with that kind of error.
Yikes. Okay, so how does HSMR compare on that same metric?
In striking contrast, HSMR achieves a remarkable 0.0% violation for elbow rotations beyond 10, 20, or even 30 degrees of unnatural bending. 0%.
Zero.
And for knees, which also have limits, it shows only minimal violations. For instance, maybe 0.2 to 0.5% for rotations exceeding 20 degrees, depending on the exact threshold.
That is incredibly compelling. That quantitative evidence really demonstrates HSMR's unique ability to ensure physically plausible joint movements.
It does. It's not just about looking better subjectively, it's about being fundamentally scientifically correct in its motion representation.
And beyond the accuracy and the biomechanical soundness, what about speed? Is it practical?
Yes, that's another advantage. HSMR, being an end-to-end deep learning approach, is dramatically faster than previous methods that tried to fit the Xiaol model using optimization techniques.
That much faster.
Those older optimization methods could take up to like 3 minutes per frame to fit the Xiaol model. HSMR delivers results from a single image in, well, fractions of a second on a GPU. Mere seconds at most for practical purposes.
Wow. So it's not only more accurate and biomechanically sound, but also way more practical.
Significantly more practical, yes. For real-time applications, for processing enormous data sets, this makes it a tool that can actually be deployed effectively in research and potentially industry right now.
Okay, so let's wrap this up. What does this all mean for us, for the field? HSMR seems like a really pivotal step, a true academic advance in 3D human reconstruction.
I think it is. By meticulously integrating a biomechanically accurate skeleton model like Xiaol, and then cleverly overcoming that huge lack of direct training data through pseudo ground truth and iterative refinement.
The Xiaolify process.
Right, Xiaolify. It delivers 3D digital humans that don't just look human, but crucially move human. It successfully bridges that critical, long-standing gap between sophisticated computer vision and the really stringent demands of biomechanics.
The relevance to you, the listener, and so many fields seems immense then.
Oh, it is. Imagine the applications. More realistic characters in games and films? Sure, that's the obvious one.
Yeah, better animation.
But think beyond that. Powerful new tools for sports science. Analyzing athletic performance with unprecedented anatomical precision. Helping athletes improve technique, maybe prevent injury.
Or rehabilitation.
Exactly. Imagine rehabilitation specialists designing personalized physical therapy exercises that precisely respect actual joint limits, guiding patients safely and effectively through recovery. The system inherently understands what's safe.
And robotics too, teaching humanoids.
For sure. Enabling us to teach humanoid robots more natural, fluid movements that are biologically plausible, not just visually plausible. The academic rigor here really sets a new standard for what's possible.
This is fascinating. It truly raises an important question for the future, though, doesn't it? While HSMR makes these incredible strides, especially with its clever pseudo-ground truth and refinement, it still largely relies on estimated data for training.
That's true. The initial pseudo-truth comes from SMPL estimates.
So what new breakthroughs could we see if we actually had truly precise, perfect 3D labels for a vast data set of human movements, captured with, I don't know, highly accurate motion capture systems combined with medical imaging?
That's the dream data set, isn't it? The potential leap forward could be enormous if we had large-scale, truly accurate scale ground truth. It could refine these models even further.
And beyond just training data, how could these biomechanically accurate models be integrated even more deeply? Maybe directly into advanced simulation environments like OpenSim?
That's a really exciting direction, not just using them to analyze movement after the fact, but to actively encourage and predict physically plausible motion in real time within a simulation.
So the simulation itself enforces biomechanics.
Right. Perhaps even suggesting movement improvements or preventing simulated injuries before they happen. The journey to truly lifelike digital humans, ones capable of performing and understanding the full complexity of human motion. Well, it feels like it's just taken a really significant step forward, but there's still a way to go.
An exciting frontier where AI meets anatomy. It seems the journey has just begun.